So those ones you did on your homework last night where dy dt is equal to ky is part of something called the law of exponential change. And what's happening is the rate of change of a quantity y is proportional, that's where we get the k from, to how much of y you have. This happens in a whole bunch of applications. Certain chemical reactions work this way. Populations, at least initially, grow this way, not long term. But there's exponential growth. Or it could be exponential decay. If you're doing half-life, this also works. The rate at which the radioactive isotope decays is proportional to how much there is. Okay? So, let me show you that it turns out, we'll go through this. I'll lead you through the steps. We have dy dt is equal to k times y. So just like we were doing, we divide by y, we multiply by dt. So we have the integral of 1 over y dy is equal to the integral of k dt. So we'll have the natural log of the absolute value of y is equal to kt plus c. Raising both of those as exponents on e, and since y is a positive quantity, we can drop the absolute value, so y is equal to e to the kt plus c. We talked about yesterday the fact that we can rewrite that as e to the c times e to the kt. So I wrote c1 here just to say, look, this is a different constant than it was before, but there's really no reason to keep track of the fact that it's a new constant. I have graded some AP exams where someone kept track of every time they did something and they did multiple things. It was like C5 by the time they got finished, and I'm like, there's really no good reason to do it, but okay. It wasn't wrong. I just had to slog through it and make sure they didn't make any mistakes on the way. So if y is equal to y sub 0, so that's a constant when t is equal to 0. So they're telling you when t is equal to 0, there was this much of the substance. Substituting in, we get y sub 0 is equal to c sub 1 e to the k times 0. So y sub 0 is equal to c sub 1. So what we get is this general rule for exponentials. If you have exponential change, which is where the derivative is proportional to the amount of a quantity that's present, this is always going to be your equation. And it allows you to do it without doing separation of variables, which is why you pretty much never see these on the AP exam anymore, because you don't have to go through all this. You can jump through straight to the ending. You will see a lot of separation of variable problems. Not a lot of, but you'll see them every year pretty much. So that allows us to solve something like this much quicker than you did on last night's assignment. All you have to do is go, okay, recognize this as being exponential change. That's the differential equation for exponential change, which means that my equation is going to be y is equal to y sub 0 times e to the kt. My initial quantity at time 0 is 10. So that means y is equal to 10 e to the kt. The value of y when t is 30 is 50. So substituting that in, we get 50 is 10 e to the 30k. Dividing, we have 5 is e to the 30k. Taking the natural log of both sides, we have the natural log of 5 is equal to 30k. So the natural log over 30 is equal to k. So now my equation is y is equal to 10 e to the, typically it's written as t times the natural log of 5 over 30. And notice on that, again, this is why you don't see these on the AP exam much anymore. You see something that's like it, but not quite this. You used to be able to see ones just like this, is you can solve it, and I haven't used a lick of calculus on it. Everything that I did was use a formula that I knew and then some pre-cal stuff. Okay, so again, that's why you don't see these much anymore. They're good as an introductory thing for separation of variables, but past that, they're not much good, at least not for testing calculus knowledge. All right, moving on to page 2. So we already talked about this. This is law of exponential change is one type of separation of variable problem. So let's do a separation of variable problem. So here I want to separate the variables. I want all the x's and dx's on one side and all the y's and dy's on the other side. Whatever shall I do? I mentioned this yesterday. Factorize. Yeah, factor. Specifically, we can factor out an x squared. dy dx is x squared times, and here's a place that students sometimes make a mistake, times what? No one wants to answer because I said, here's a place that students sometimes make a mistake. You should think of that as an opportunity to go, well, maybe I'll make the same mistake everybody else made. And Mr. Davis will go, yeah, that's the mistake people make. So it's okay.
Y squared plus 1.
Yeah, it's y squared plus 1. What do you think someone might do accidentally?
Put y squared.
Just put y squared. Because they're like, oh, the x squareds cancel out. That is the most common mistake.
I was about to say it. I thought myself.
Okay, so now I'll divide both sides by y squared minus 1 and multiply both sides by dx. So I get dy over y squared plus 1 is equal to x squared dx. Now we'll take the antiderivative of both sides. What would the antiderivative of dy over y squared plus 1 be? This is not a figure it out, this is a recognize.
Tangent inverse.
Yeah.
Y.
This is the arctangent, or the tangent inverse, either one, of y is equal to
X cubed.
plus c. Eventually I want to solve this for y, but first I want to find the value of c unless this has a logarithm in it. If it has a logarithm, I'll wait, but if not, I'll go ahead and do it. So substituting in, we have the arctangent of 1 is equal to c. Now you get to show me how good you are at the unit circle. What is the arctangent of 1? Nice. Because tangent at pi over 4 is equal to 1. So we have arctangent of y is equal to 1/3 x cubed plus pi over 4. And I want to solve that for y, so I'll take the tangent of both sides. Y is equal to the tangent of 1/3 x cubed plus pi over 4. Notice in this case that the c ends up getting buried inside of this function. It's not blah, 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 plus a number. That frequently happens. All right, let's take a look at this next one. Oh, any questions about that one? All right. This was part of an AP free response question from several years ago that just torched people. It's not super hard, but it is easy to make a mistake. This is one where it's close to being, k times b, but it's not quite k times, it was dy dt is equal to k times y. It's not quite, so you have to work it out. That's what I was saying. You'll see ones that are similar, but not quite. I think part of the reason it torched some people is because they assumed that it worked the same way, and it doesn't. It's close, but not quite. So separating the variables by dividing by 100 minus b on both sides, we get db over 100 minus b is equal to 1/5 dt. So the right side integral is pretty easy. That's just 1/5 of t plus c. It's the left side that's a little more difficult. This is going to be the opposite of the natural log of the absolute value of 100 minus b. So let's think about that just a second. If you just had the natural log of the absolute value of 100 minus b and you took its derivative, it would be 1 over 100 minus b times the derivative of 100 minus b, which is negative 1, which would give us the opposite of what we want here. That's where this negative comes from, and that's, again, part of what torched some students on this, is they miss that negative sign, which is really easy to miss. With logarithms, I do not solve immediately for c. I'll go ahead and isolate the variable b. So I'm going to multiply both sides by negative 1. So I'll have the natural log of, and by the way, since b is equal to 20 at the time in question, I'm going to drop the absolute value right now, because 100 minus 20 is going to be 80. So this will be 100 minus b is equal to negative 1/5 t. And if you really want to make it minus c, you can. But if you divide c by negative 1, well, you just have made it a new constant. So again, if you really want to make it minus c, you can, but it's not worth the time, I don't think. So now we'll use both of these as an exponent on e. So this will be 100 minus b is equal to e to the negative 1/5 t plus c, which is e to the negative 1/5 t times e to the c. Again, making e to the c a new constant, I'll have 100 minus b is equal to c times e to the negative 1/5 t. You can go ahead and solve for b, but at this point, now that I've gotten rid of the logarithm and have simplified both sides, I think this is the easiest place to solve for t. Because when you substitute in that t is 0, what does e to the negative 1/5 t go to? The negative 1/5 t goes to 0, so e to the
Oh, 1.
goes to 1. So we're going to have 100 minus 20 is equal to c times 1. So c is equal to 80. So now our equation is 100 minus b is 80 e to the negative 1/5 t. If I subtract 100 from both sides, I get the opposite of b is equal to negative 100 plus 80 e to the negative 1/5 t. Divide everybody by a negative 1, and b is 100 minus a 80 e to the negative 1/5 t. Any questions about that? Okay, then that is it for today. I have a worksheet for you.